Welcome to Unit 8, Lesson 1, L'Hopital's Rule. It looks like L'Hopital's, but it's pronounced L'Hopital's. To understand L'Hopital's rule, let's first look at some examples of limits. Remember, we learned about limits in Unit 1 of this class. Example 1. Limit as x goes to 0 of e to the x over x squared plus 4. For a question like this, we can just plug in the zeros. So when we plug in the 0, as x approaches 0, that's e to the 0 over 0 squared plus 4. That's equal to 1 over 4. That's it. So to find limits, if we can plug in, we just plug in. Next one. The limit as x goes to infinity of x cubed over x squared. We can plug in, because if we plug in infinity, we get infinity cubed over infinity squared, which is equal to infinity over infinity. But that, we don't know what that is going to be. It's indeterminate. But we can simplify our expression first. When we do that, x cubed divided by x squared, that's just x. So the limit is just as x goes to infinity of x. Well, now we can plug in the infinity. So the second limit goes to infinity. Number 3. The limit as x goes to 3 of x squared minus 4x plus 3 over x minus 3. If we plugged in, that wouldn't work. 3 squared minus 4 times 3 plus 3 over 3 minus 3 gives us 0 over 0. That's, again, we don't know what that is. We can't do 0 over 0. So instead, we can simplify again. We can factor the top. X squared minus 4x plus 3 is just x minus 3, x minus 1 over x minus 3. So the limit as x approaches 3, well, the x minus 3 terms cancel, and we end up with the limit as x approaches 3 of x minus 1. Now we can plug in, that's 3 minus 1, which is equal to 2. So these are different ways of evaluating, figuring out the number for limits. But as we have noticed, sometimes we get infinity over infinity, or say 0 over 0. Those we don't know. We need different ways of evaluating those limits. L'Hopital's rule, today's lesson, gives us another way. To help us understand this, let's think about this one. The limit as x goes to infinity of e to the x over x. If we plug in, that doesn't work, because if we plug in, that gives us the e to the infinity is infinity over infinity. We don't know what that is. Okay? But we can think about how big these numbers are. Let's look at the top and the bottom. The top is e to the x. The bottom is x. When x equals 1, 10, 100, and 1000. Well, when x is 1, e to the x is about 2.7. That's e. When x is 10, e to the 10th power is about 22,000. When x is 100, e to the x is about 2.7 times 10 to the 43. That's 2, 7, and then 42 zeros. When x is 1,000, it's really big. E to the x is just, the top is really big. So what would our ratio be? E to the x over x. Well, when x is 1, it's just e, 2.7 or so. When x is 10, it's going to be 22,000 divided by 10. That's about 2,200. When x is 100, e to the x over x is going to be about 2.7 times 10 to the 41. So we can see this ratio, e to the x over x, does get bigger and bigger and bigger. When x is 1000, this ratio will be really big. So the limit of this ratio really is in fact equal to infinity. Now infinity over infinity doesn't have to equal infinity. It could equal infinity, it might equal 0, it might equal 1, it might even equal something like negative 3/5. We don't know. But for this question, e to the x over x is equal to infinity. Why? Because e to the x is growing much more quickly than x. In other words, if f of x is e to the x and g of x is equal to x, then f prime is greater than g prime. The top is growing faster than the bottom. L'Hopital's rule says that when we have infinity over infinity, or say 0 over 0, we can actually look at, instead of looking at the limit of f over g, we can look at the limit of f prime over g prime. That tells us the limit. We just take the derivative of the top and the bottom. For example, with e to the x over x, L'Hopital's rule says we can just take the derivative of the top. The derivative of e to the x is just e to the x divided by the derivative of the bottom. The derivative of x is 1. So we end up with the limit is really equal to the limit as x goes to infinity of e to the x. Plugging in infinity, e to the infinity is just infinity. That's why we know that in this problem, the limit as x goes to infinity of e to the x over x, that's equal to infinity. It's not always infinity. Here's another example. The limit as x goes to infinity of e to the x over x squared. Well, this one is still infinity because we take the derivative of top and bottom. The derivative of the top is still e to the x. If f of x is e to the x, then the derivative is still e to the x. But if g of x is x squared, the derivative of x squared is 2x. We still can plug in because they're both going to infinity. E to the infinity is infinity. 2x when x is infinity. So what do? If it doesn't work, we take the derivative again. The second derivative of f is e to the x still. The second derivative of g is 2. So we know then that this limit is equal to the limit as x goes to the infinity of e to the x over 2, which is equal to e to the infinity over 2, which is really just infinity. So we can take the derivative of the top and the bottom as many times as we want. Next one. The limit as x goes to 0 of e to the x minus 1 over sine x. We can plug in. The top and the bottom are both 0. So we have to take the derivative of the top and the derivative of the bottom first. The top is e to the x minus 1. The derivative of that is just e to the x. The bottom is sine x. The derivative of that is cosine x. So the limit as x goes to 0 of e to the x minus 1 over sine x is really just equal to the limit as x goes to 0 again, as x approaches 0, the derivative of the top, which is e to the x, divided by the derivative of the bottom, which is cosine x. Now we can plug in, that's e to the 0 over cosine 0, which is 1 over 1, which is 1. That's how we apply L'Hopital's rule. All it says is take the derivative of the top, the derivative of the bottom. We can do that. Okay, derivative of the top, derivative of the bottom, and then evaluate the limit. Next example. The limit as x goes to infinity of 5x squared plus 4x plus 3 on top over e to the x minus x squared on the bottom. Okay. Well, the top is 5x squared plus 4x minus 3. The derivative of that, if we plug in infinity, they both go to infinity. It doesn't work. Well, also on the bottom, we get infinity minus infinity, which we don't know what that is. So we take the derivative of the top, which is equal to 10x plus 4. The derivative of the bottom, which is e to the x minus 2x. Still doesn't work. Derivatives still go to infinity. We take the derivative again, the second derivative. The second derivative, well, we go from 10x to just 10. G prime x is e to the x minus 2x. That's the derivative of the bottom, e to the x minus 2x. The second derivative is going to be e to the x minus 2. So after taking the derivative on the top and the bottom twice, we get that the limit, this is the limit as x goes to infinity of 10 over e to the x minus 2. Plug in infinity and I get 10 over infinity, which is 0. It's like saying we have a cake, we cut it an infinite number of slices. How much will we have if we have 10 slices? Well, 0, because the slices are infinitesimally small. Here's a tricky one. This is the last one we'll look at in this video. The limit as x goes to infinity of sine x plus x on top, x on the bottom. Okay, let's use L'Hopital's rule, because if we plug in, they're both infinity on top and bottom. The derivative of the top is sine x plus x, so the derivative is cosine x plus 1. The bottom is x, so the derivative is 1. The problem is, as x goes to infinity for our derivative, we get cosine of infinity plus 1. And cosine fluctuates. There's no single point it approaches. So it doesn't work. L'Hopital's rule is not working. If we want to take the second derivative again, we can. We will get negative sine x for f and 0 for y. But still doesn't work, because as x goes to infinity, sine x or negative sine x is undefined. So we can't use L'Hopital's rule. So to figure out this derivative, we cannot use L'Hopital's rule. We can't use it. Okay? So what this really shows is L'Hopital's rule only applies when the top and the bottom, f and g, are both differentiable. We can find the derivative, and the limit must exist. We must have that limit. Alright, that's it for this.